This is the first episode of our tutorial series Electricity 99. It was labeled that because it's even more basic than Electricity 101. Everything on Earth is made up of atoms. That is significant because there are currently only 118 known atoms. All solids, liquids, and gases are composed of these atoms. It is amazing to think that everything is made up of just these 118 little parts. You, your house, your pets, everything. This seems very elementary, but we want to get even more basic. Atoms consist of only 3 parts. Therefore, everything in the universe is made up of only these parts. Those 3 parts are electrons which have a negative electrical charge, protons which have a positive electrical charge, and neutrons which have no electrical charge. The neutron is not charged but has a very significant role. It holds the nucleus of an atom together, which is the center of the atom. Since protons are all positively charged, if they were the only thing in the nucleus, they would all scatter. It is the neutrons that are also in the nucleus that hold the positive protons together. This is because of the strong nuclear force between these particles. If you were to take protons and line them up one next to another, there would be 15,100,000,000,000 per inch. The neutron is about same size as the proton, so they are extremely small. The electron has a mass that is 1/1836 the mass of the proton. It is very small even when compared to protons and neutrons. It is hard to imagine that particles so small can be so significant to everybody and everything. The simplest atom is the hydrogen atom. It has 1 proton and 1 electron that is going around it. You will typically see an illustration with an electron going in a circle around the proton. This is not what is occurring. The electron travels randomly about the proton in a shell at a distance from the proton. You can think of it as forming a cloud about the nucleus. In this illustration, the proton is the center gray mass, and the electron forms a yellowish cloud around it. Let's look a little closer at the hydrogen atom. We can calculate some approximate values just to give us an idea of the size of the atom. For example, if the proton were the size of a golf ball, the electron, which is about 1/2000th of its size, would be moving randomly at about 8/10ths of a mile away. In other words, the hydrogen atom and all other atoms are mainly empty space. Some of you may wonder why, if atoms are mainly space, you can't see through them. It is all about perspective. If you were the size of a neutron looking around, you would see mainly space. When you're on a different scale as we are, it appears to be solid or liquid. If we take hydrogen atoms and line them up side by side, it would take 240 million per inch. That is extremely small. The electron is moving at a speed of 4.9 million miles per hour in a random fashion around the proton. Admittedly, they are not circling, but I just wanted to calculate how fast it would be going if they were. It would be going 390 quadrillion RPMs. If you consider that a merry-go-round may go 10 or 20 RPMs, this is an astonishing rate. Let's move up one level to the helium atom. This atom has 2 protons at the center and 2 neutrons to hold them together. To keep it electrically balanced, it has 2 electrons traveling in a shell around the nucleus. Even though we have drawn it this way, we should still think of them as forming a cloud around the nucleus. Moving on to the next level would be the lithium atom. The lithium atom has 3 protons with 4 neutrons to hold the nucleus together. To keep it electrically neutral, there are 3 electrons. What's interesting is that 2 electrons are traveling in a shell closer to the nucleus, and 1 is traveling in a shell further out. This is what happens with other atoms. There are multiple shells with some electrons in each shell. Scientists have a little different way of drawing this. They represent a nucleus with the number of protons, 3 in this case, and then an inner shell with 2 electrons and an outer shell with 1. In the future, this is the way we will start drawing atoms. You may ask what water is. Water is a molecule, and it is made up of atoms. Almost everything around us is made up of molecules, not just simple atoms. It is the atoms that make up the molecules, and it is electrons, neutrons, and protons that make up the atoms. In the case of a water molecule, it's 2 hydrogen and 1 oxygen atom. You may have heard H2O, that is where the symbol comes from. When it forms a molecule, the electrons start moving in random order around the 3 atoms. That is what bonds them. They share the electrons, which are no longer dedicated to one atom or the other. We have learned something about atoms, but we haven't learned what electricity is, which is our purpose. We are going to look at that now. Electricity is the fundamental form of energy observable in both positive and negative forms, which is expressed in terms of the movement or interaction of electrons. That definition came from Webster's pretty much verbatim. Basically, electricity is electrons, and more specifically electrons in motion. The movement of electrons is what we call current. If you remember the golf ball example, the electron was 0.8 of a mile away. We saw that atoms are made up of mainly empty space. It would seem very easy for electrons to be able to move through atoms in all that free space. That is not what happens, and we're going to go into how it actually happens soon. First, I'd like to define 2 concepts. Electrical resistance is a property of materials that measures how strongly the atom, in this case, resists electrical current. In other words, how unfriendly or how stingy it is with sharing its electrons. The inverse of electrical resistance is conductance. It is an atom's ability to conduct electrical current. To understand how electric current is conducted, let's look at the copper atom. This drawing of a copper atom was from the Iowa State University website. As you can see, this copper atom has 29 protons and 35 neutrons in the nucleus. It has 4 shells with 2 electrons in the inner, 8 in the next one, 18 in the next one, and 1 in the outer shell. The outer shell is called the valence electron. Electrons of all atoms in the outer shell are called valence electrons. This is important because these are the electrons that move between atoms, causing electricity to be conducted. Copper is a very good conductor, as are gold and silver. Each of these has 1 electron in the outer shell, in the valence shell. The conductivity of an atom is a function of how well these valence or outer shell electrons are bonded to the nucleus. Next, we have an illustration of copper atoms inside a wire. If you watch the video, you can see the outer electrons switch from atom to atom. Assume we take a copper wire, the copper line, and paint 1 electron green so we can observe it over time. If we marked its position and then came back 24 hours later, we would see that electron was still traveling around the same area. The valence electrons are moving within the wire, but they are not going anywhere. It is unbelievable to think the electron is traveling almost 5 million miles per hour, but it doesn't get anywhere. If we apply a potential, for example by placing a battery across the wire with a negative terminal on one end and a positive terminal on the other, the electron will start moving down the wire. In other words, the electron's motion will now not just be in one area, but it will start migrating down the wire. This is electricity, electrons in motion. We call this type of motion direct current, DC. To be thorough, let's look at what happens when we have an AC or alternating voltage. Here the voltage goes from plus to minus, and so on. The electron keeps going back and forth within the wire. Sometimes electrons are pushed out one side and sometimes they are pushed out the other side. For thoroughness, we should talk about electron flow. If we have a battery and a light, the direction of electron flow is from out of the back of the battery or the negative side through the light bulb and back into the positive side. While this makes sense, the conventional or the classical form of current flow is labeled out the plus side down through and into the negative side. Historically, some say that Benjamin Franklin is the one that got it wrong. He thought that positive charges were the ones that move. At the time they didn't know anything about electrons, and they didn't know the details of atoms. Back then he thought that probably it was the flow of positive charges. He labeled it this way. By the time they figured out the concept of electrons, and electrons being the electricity, and electrons being a negative charge, this convention had already been accepted and it was never changed. I hope you found this video interesting, but what should you remember from it? You don't have to remember any of the numbers, those were just presented to show you how small atoms, neutrons, protons, and electrons are. They were to give you an idea of what an atom is and how the electrons move from atom to atom. I would like you to remember that there are really two types of atoms. They are the friendly sharing low resistance atoms which will easily share their valence electrons, and the unfriendly stingy high resistance atoms that don't like to share their valence electrons. Also, if there is no voltage potential applied, electrons stay in their neighborhoods and may go neighbor to neighbor, but they don't move outside their neighborhood. When you apply electrical potential to the two types of atoms, the electron sharing among the low resistance atoms is much faster. There is a greater current flow or electron flow in those atoms. Electricity is electrons in motion and electron flow is controlled by the resistance. Since this is the most important item to remember, we will say it once again. Electricity is electrons in motion and electron flow is controlled by the resistance. Thank you for watching this video and we hope you continue to watch the Electricity 99 series.